We'd then design an experiment to test our hypothesis. And then we said, probably the most important step, what happens now? It fails. Right? And we end up sitting in this kind of crappy loop of failure, hypothesis, experiment, failure, hypothesis, experiment, failure. Okay? This is why a lot of people leave science, because all they get stuck in is in that permanent loop, and that's all they get is just failure. Okay? I'm not going to lie, that sucks. Okay? But the one time it works, it's a beautiful ecstatic feeling, and you keep driving forward through the rest of it. Okay? After you drive through, that's where we end up now into kind of two potential categories, either scientific theory or natural law. Okay? Theories can be constantly refined. As we discover more information, we may decide that we need to adjust that theory, okay? Or the rules that we've come up to describe what we've seen, because we're missing something. It doesn't account for all observations. And that's one of our goals, is to come up with a unifying theory that covers everything, kind of like a law. Okay? The laws are always true. Okay? This does not mean we don't trust theories. Theories have direct experimental evidence that supports that they work. Okay? Chemistry's role in kind of all of this is kind of to bridge the gap. And depending on who you talk to, you'll get different things on this perspective. But you end up with the mathematicians and the physicists who are ultimately bogged down in kind of the numerics, particularly the mathematicians. Mathematicians play around with numbers and go, ooh, that's cool, I made a new number. Okay, fun. It's a little bit more involved than that. Okay? Physicists go back and look at what the mathematicians did and said, that's really cool that you made a new number that you thought didn't apply to anything. But I can see how that applies to now something in the physical world. So the physicists take what the mathematicians went through and just did as kind of mental nonsense and actually make it real. And then the chemists, or then the physicists, try to sell this information off to engineers, okay, or biologists. Hey, you can do some really cool things with this. But physicists are too grounded in the mathematics side. Sorry if there's any physicists here. I love them to death. But they're often too grounded in the mathematical side that they can't explain what's going on to the real world. Okay? They're too involved in the theoretics of what's going on. Meanwhile, your biology, your engineers, and all of that are too involved in the real world to necessarily see what's going on the theoretical end of it. Right? So something needs to bridge that gap. And that's where chemistry kind of comes in. Chemistry came in as making those simple observations and trying to tie them and make sense of them. So they started to pull from whatever they had access to, the real world and the crazy weird stuff the mathematicians came up with. And they kept trying to play this matching game until something worked. When something works, they can then advance, move forward, and we come up with new discoveries and new thoughts within chemistry, biology, physics, all of that fun stuff. Okay? So chemists kind of bridge that gap. What particular gap they're bridging depends on the field of interest. Okay? Chemistry subcategorizes into several different sections. You get organic chemistry, my favorite, biochemistry, too much biology to be favorite, inorganic chemistry, they do some pretty cool stuff with that, and physical chemistry. Okay? Those four major branches then get enveloped in the concept of general chemistry, sometimes referred to as quantitative chemistry. Okay. So what we are studying is not just chemistry as a general field, but each of these individual categories, people spend their lives studying. And now what we're doing is telling you, each of those individual people that spent their lives studying it, you are now going to study all of them in 16 weeks. It's a bit daunting. But we also aren't going to go into the level of detail that the physical chemist does, thank God. Okay? They have an incredible amount of mathematics that is beautiful to watch someone solve, but it is incredibly difficult to do on your own. Okay? The inorganic chemists tend to apply to inorganic materials. Well, what is organic versus inorganic?
Organic contains carbon.
Okay? One of our simplest definitions is that organic has the element carbon, and inorganic uses everything else. Well, that's a bit boring. Okay, that's saying that only carbon can be used in organic? No. Okay. A lot of other elements can be involved in organic chemistry. Carbon just happens to be one of the primary sources. Does that mean all carbon sources are organic?
No.
Nope. Diamond, very clearly defined as an inorganic species. But diamond is carbon. Okay? So the categories don't have simple breaks in them. They have these kind of crossovers between them. That's because they're all belonging to chemistry. And depending on what level you're trying to get at, you may need varying blends from each of those fields. Biochemistry, which is a fun one, sort of fun one that I'm teaching this semester, is a blend between the biology aspect and the chemistry aspect. And depending on how you are taught biochemistry, you are taught it either as a biologist, in which case chemistry has no role. It's a bit overdramatic. Okay. Or you're taught it from the chemical perspective, in which case biochemistry is organic chemistry. Very little difference. Okay. In general, what we're looking at with an organic chemist is someone going into the lab, mixing some solutions to make something cool. Biochemistry, someone goes into the lab, points at a beaker and says, do something cool. Okay. We're far enough advanced that we can do that. We can point at the beaker and it does something cool for us. It's one of the reasons why I don't like biochem, because I didn't do it. I told something else to do it. Okay. Organic is a lot more hands-on in that respect. Okay. So we get these larger fields. That's what we're working with. That's what we're trying to understand and study. Okay. Before we can understand where we're going, we have to know where we came from and all the rules that built up to it. Okay. That's largely what we're getting through in this semester, is that big overview, so that you're aware of what the terms are, so that when you see them in the future, you have a vague general idea of what they are, and you can now talk about how and why and all of those big, larger questions. This is the base level. Kind of make sense? I'm going to take that as a yes. So, that was chapter 1. Exciting stuff. So, don't forget the Canvas syllabus quiz, just because that's in there. We move to chapter 3. Chapter 3 is now starting to look at matter. Okay. Well, what is matter? Go for it. What do you think? What is matter?
Something with mass and occupied volume.
Okay, something with mass occupies volume. It's everything that we have to work with. Okay? And so what we did initially as scientists was trying to come up with definitions on matter and come up with ways that we could classify and grab a hold of it, wrap our brains around it. Okay? Well, there's two ways that we could potentially wrap our brains around it. We have this qualitative observation and a quantitative observation. And when we're looking at chemistry, that's what we're going to be evaluating each and every time. What is our qualitative observation? What is our quantitative observation? Okay. What do each of those mean?
Does it qualitative mean it's observable? Quantitative means it's just a figure or a amount?
Okay, we'll work with that. Qualitative is observable. Quantitative is an amount. How would you get a quantitative value?
For matter?
Yeah.
Isn't there a bunch of matter out there that's supposed to be there, but it isn't? In space?
True. How do you get me an amount on that?
Mass.
The way I think of it is like qualitative is more of like senses, and then quantitative is like a number. So if you take like some kind of equation or something like that and do it, whereas qualitative, like you're observing what it looks like, the smell, the color change, that kind of stuff.
Okay. It's a good way to look at it. Senses versus numerical values. I was going to call you out, but she's already pushed far enough away from it. We're observing in both cases. Okay. To figure out a quantitative, you added in mass. How do you figure out the mass of a piece of matter? How do you figure out the mass of yourself? Doing what? How do you weigh? How do you weigh yourself?
On a scale.
Okay, so what do you do with the scale? You stand on it, then what do? You observe the numbers it's reading, right? So we're still making an observation with both qualitative and quantitative. So observation isn't quite going to cut it in this case. We really want something kind of more general. So our qualitative are kind of our general ideas, okay? Whereas our quantitative are very much numerical. Okay. Something that we can directly measure. Qualitative becomes very hard to measure because that's going to be dependent on every person that's looking at it. For instance, hold it in your head for a moment here. What color shirt am I wearing? Everybody said the exact same color, right? I heard teal. I even heard green. That one was a little new to me. I heard blue. Okay. It's a turquoise. It's a qualitative observation. That observation is not going to be consistent for every single person. So if we're going to look at which is more useful, what might we say? Quantitative, but that's me fishing for the wrong answer. Okay. Both of them are important. Both of them allow us to draw conclusions about the world around us. Depending on what we need to get out of it, we may have to rely on more one than the other. But you should never rely on just one. Okay. Because the quantitative measurement comes down to how we've measured something. If I step onto a scale to measure my weight and it says I am 600 pounds, does that mean I am 600 pounds?
No.
Thank you. Okay. There's something wrong with the scale. I have to use my qualitative observation that I am not 600 pounds to then evaluate the quantitative one and say there's something wrong here. Either my head is way off in a different world, thankfully it's not, okay? Or there's something wrong with the scale. I have to be able to evaluate both. Okay? Checks and balances all the way through. Okay? What's that? More gravity increased for as far as weight goes. So qualitative observations. What is roughly 70 to 80% of all life? Water. Okay. In fact, as far as life goes as we're concerned, water is our most important chemical or most important molecule. Okay. Why is water probably the origin of all of our qualitative observations? Okay, we need it to survive. Not only is it everywhere, but when we think about matter and we classify matter, what types of, without trying to say the word, what types of matter are there? Maybe that works. Liquids, solids, gases. Why is water an interesting one? On this planet, we have access to all three relatively quickly and easily. Okay. We have all three phases. And some of those phases look boring in pictures, so I just kind of had to make it up as I went. So in that first picture, what do we have? Solid, you're right, it is snow. And that next one, I know we still have snow. Give me a break. Aiming for the liquid. Wow, those eyes don't show up so well. And the last one? And the last one, we're aiming for gases. Okay. Are there any properties that we could then use as our qualitative observations of these individual phases? For instance, maybe shape? Volume? I think your textbook even drops in compressibility. Whoops. 2 S's? 2 S's, really?
Yes.
Oh, that looks ugly. Okay. So we could go through and look at some rather simple kind of classifications for each of these and try and come up with observations of them. Are they all three phases giving us the exact same results? So pick a phase, pick one of those three things. Solid, what are you going to pick?
Shape.
Okay. What are you going to tell me about the shape of a solid?
Hopefully snow is just the different shapes and snowflakes.
True, so you can change the object of the solid, but if I put down the solid down on the table, what happens to its shape?
Oh, it doesn't change.
What happens to the liquid?
On top, it spreads.
And our gas?
It expands.
Okay. It will fill the container that it's in. And now we've got kind of an issue here. Notice for shape, I said fills container for both liquid and for gas. Is that really true?
Depends on the container.
Okay. Let's take this room and add 5 milliliters of water to it. Okay. Roughly how much is 5 milliliters? Let's change it. Your soda bottle. We got everything we can think about. Soda bottle. We take a soda bottle. Please don't pour it, but let's just pour it into this room. In the shape of this room, where is it going to go?
Anywhere it fits.
Anywhere it fits. So when you pour that liquid, it's going to fill up the space above our heads.
Well, anywhere on the ground that it fits.
So it will fill the container up to the volume of the liquid. Which will become a little bit more relevant when we shift to volume. What is the volume of a solid?
Don't they not have volume?
It's not that they don't have volume. This pen occupies space, which means I can't be in the exact same space as it. It has a volume that excludes me from it. So solids do have volume.
It's just whatever the volume of that object is.
Doesn't change. Okay. It is the volume of the object. It does not change. What about the volume of a liquid?
It doesn't change.
It also doesn't change. Its shape can change depending on the container that's holding it, but the volume of that liquid never changes. What about a gas?
Changes the space of the container.
The volume of the gas is dependent largely on the shape of the container. So it completely fills the container. Its volume is mutable, it's changeable, which then can shift us into the next compound, or the next thought, compressibility. So compressibility, when I try and compress a solid, what happens? If we go to the gym, we do it all the time. Why do we do it? So that we get stronger, because the solid never compresses. By forcing or attempting to force it to compress, we can then build our own strength. So our solids do not change as far as their compressibility. Let's just say null. How about liquids? Should be writing liquids. What happens when you try and compress a liquid?
It'll stay.
Doesn't really change either. We're also looking at kind of a null set. What happens to the volume? Or sorry, this is what happens when you try and read and write at the same time. What happens to the gas? When you try and compress a gas,
It wouldn't change.
gases can't be compressed. We've got a bunch of air in here. What happens if we close off the room and shrink the room down? Is that air still contained within it?
Yeah.
Did I compress by changing the volume? Yep. So gases can compress. So we'll call it, I guess, a yes. Okay. They do have this compressibility feature. Okay. What happens if we now take this information and try to draw it as an example of what's happening down at the molecular level? So we're now going to say our water molecule is just a little circle. In the case of the solid, okay, that's only a single water molecule. To have a lot of solid, I need a lot more circles, a lot more water molecules. Where should I draw the next water molecule? I'm tired of drawing circles, so I'm going to stop. What about a liquid? A little bit more space, but they're still pretty close to each other. And what happens to a gas? Lots and lots of space, virtually no contact between them. All of those observations we made about thinking about what happens to the shape or the volume or our compressibility can now come into play in our pictorial representations of the individual molecules that make up those species. Okay? It is that visualization that we try to work with when we deal with chemistry. Kind of, sort of? When did we start? Okay. So, matter. We've got these individual phases. We can then also further separate these into different kind of categories. We have a mixture of different matters, and we can also have a pure substance. Okay, well, how do we know we have a mixture or a pure substance? Well, it might come back to what we're looking at. A mixture is spatially linked. A pure substance is chemically linked. What was the name of this class? Chemistry. Okay. So you're in this class because you already know what chemistry meant. Right? So when we say chemically linked, you're like, oh yeah, of course. That makes perfect sense. Okay. We're running into an issue with definitions. What we're trying to do is give you this overarching idea of what things are possible or what things can happen, but we run into this issue of defining our terms with the definition. Okay? Very cyclic. It's not a good idea. It doesn't work out so well. So remember that we will be addressing what these extra terms mean when we're talking about chemically linked versus spatially linked, okay, as we continue through the semester. When we subcategorize this down, it might help us to understand a little bit more about what's happening with our chemically linked versus spatially. In a mixture, that can be dropped into two categories. Something known as a heterogeneous mixture or a homogeneous mixture. In a heterogeneous mixture, we have multiple phases. There is a visible separation. So we have a liquid mixed with a solid. Okay? We can see the solid, we can see the liquid. Okay? They are spatially near each other, but they are not mixed evenly. Meaning when I reach in and grab any random location, I can pull out a liquid in one case, or I can pull out a solid in another case, or liquid and a solid in another case. That gets me a heterogeneous system. Every time I reach in, I can get something different. Right? When we move to a homogeneous system, there is no visible separation, which means when I reach in to grab, I'm going to be grabbing the exact same things. Okay? Those things, as long as I'm grabbing a sizable number, okay, will maintain the same ratio, but they will not be chemically linked to each other. Okay? So our homogeneous examples, no visible separation. Any ideas?
Wood.
What's that?
Wood.
Wood.
No, Kool-Aid.
Kool-Aid. How did I get wood from Kool-Aid? Kool-Aid is a good homogeneous mixture, okay? Or like your sodas. Seriously, you said Kool-Aid the whole time?
Yeah.
Kool-Aid or our sodas. We'll avoid sodas for the most part, actually. We'll come back to that. Kool-Aid, which is really just a mixture of Water and sugar. We have two substances, two different types of matter that have now been mixed. And when they mixed homogeneously, where we could not see a visible separation between the water and the sugar. How about a heterogeneous mixture? Oil and vinegar, salad dressing. Okay. Why? I go to the store and I shake up or I pull out the salad dressing. Doesn't the salad dressing look all consistent in one thing?
Good. Oil doesn't mix with water.
Okay. We run into an issue with stores. You can thank chemists probably for this one too, and businessmen. It's probably businessmen's fault. If you go into a store and you see your salad dressing with two different layers, and you're like, well, there's two different layers. I don't want to bother to mix that. I'm going to buy the one where they're all mixed nice and evenly because that must be better. It's easier. How did they get the oil and the vinegar to mix? Shaking it will only do it temporarily, separate or mix them together. They had a bunch of other crap in there that causes the oil and the vinegar to mix with each other. Oil and vinegar generate a heterogeneous system. They do not mix with each other. They will separate out. Okay? Which then brings up an interesting dilemma. If I take oil and vinegar that are very clearly separated from each other and I put them in the same container, I can see those two layers. What happens when I shake it? Sure looks like it mixes. And then I would say, there's no visible separation. It should now be a homogeneous mixture, except eventually what happens? It separates back out. Okay? So depending on when you are making your observation, okay, you may be coming to an incorrect conclusion. So we have to be careful that when we're making our observations, we're making them at consistent times and at the appropriate time. How do you know what's appropriate? It's a hard question. Do it 100 times. Okay. Change the time on when you're making that observation. Do you see any changes? No changes? Okay. Fair enough. You've now established that you've got a consistent observation. Now what do we do as scientists? We've already tested it. We could go through and say it's a law or a theory. But if I come up with my own law or theory, does that make it a law or theory? Everybody else has to look at it and say that is valid. So we will go through and design our experiment with whatever controls or variables we want on it, mixing oil and vinegar and saying that's a homogeneous system. We then put that out to the rest of the world. The rest of the world has to then evaluate it and decide, yeah, that's true, or no, it's not. Okay. And what's the rest of the world going to tell us? It's not homogeneous, it's heterogeneous. Those two species don't mix with each other. Why? Hopefully we figure that out by the end of the semester. Okay. But at this point, we're tasked with just being able to qualify what it is. If we shift over to the pure substance, okay, when we're looking at our pure substance, we're saying they're chemically linked. That can still subcategorize into two different sections. One, elements. Okay. We've reduced it down to the smallest, quote-unquote, possible piece. Okay. For instance, if I take water and try to reduce that down, could I break water into something smaller? Yes. What could I break it into? Hydrogen and oxygen. I've broken it down smaller. Okay. That is our chemical linkage. Hydrogen and oxygen were chemically linked, which then puts us in a mixture. Okay. Or sorry, when we mix it with sugar. If we're now looking at water on its own, it is chemically linked. Is it a compound or an element? Water I could break into smaller pieces. That makes it a compound. What about the hydrogen and the oxygen? Can I break those down into smaller pieces? Yeah, no, we're kind of on that weird threshold there. But at this point, we'll say no. So we'd reference those as our elements. And that was our initial observations for probably, we said 800 years for chemistry. For about 700 years, that's what we had. Okay. Only within the last 100 years did we realize elements could be broken down even further. Okay. So our elements are listed neatly for us on our periodic table. Periodic. That's our big walls. Okay? So we come up with our elements, the names, all that fun stuff. Our compounds are made up of at least 2 elements. Do they have to be different elements? Not in the strictest definition of the term. Okay? A compound is a mixture of any 2 elements. Okay? It can be different elements. It can be the same element. Okay? It's depending on what we're looking at. Okay? Questions on that? I'm not seeing anybody writing, so I'm guessing this is really boring. Is that also a yes? Okay. We're doing okay? So now what we want to do is subcategorize our different elements, our smallest individual pieces, into some other categories. And we noticed that if we looked at most of our solids, they had this nice shiny color to them. And that when we looked at some of our other solids, very few of them, some of them were dull. Okay? Meaning that they didn't have this shiny characteristics to them. So we started to separate those away from each other and said, okay, solids over here that are shiny, solids over here that aren't shiny. Then we started to look at more of their properties. The next property, malleability, which is, okay, they can kind of change their shape. They deform when you hit them. Okay? Let's not use examples on that. Brittle, meaning it's not malleable. What does that mean? It breaks instead of just deforming its shape. Okay? And we started to notice that there were these consistent trends within it. Most of our solids that were shiny were also malleable. We also noted that they conducted electricity, and they had high densities, high melting points. Okay? They reacted with another species, which we won't mention yet. Let's pretend that's not there. Okay? When we looked at our other solids, they were dull, brittle. They had all the opposite characteristics of these. So in the process of looking at those, we said, okay, well, if they're different, what do I have to do? Categorize them. How do I know they're in a different category? How do you tell yourself away from everybody else? There it was. Someone said it over there. Maybe over here. You name it. We arbitrarily decided that these solids that had a high shine, very malleable, all these fun things, we decided to call metals. We look up on that left, far left up there. Oh, look at that. The title even lines up on the far left. Metals. Interesting. What about the ones on the far right? When we looked at those solids. Super creative people that we are. Those aren't metals. So we called them non-metals. And one of the things that we found was that our metals will react with our non-metals. Okay? And that our non-metals will react with pretty much everything and anything. So we've got some kind of interesting observations coming out of this. We also found that there were some species that were gases. Well, gases certainly didn't fit in our metal category because they weren't solids. They also don't fit in our non-metal category because they're not solids. So we had to move to our other observations that we made. Dull, brittle, conductivity, okay, densities. And when we looked at the sum of all of those observations, we said that those gases best belonged in the non-metal category. Okay? Which would be on the right-hand side for the column. And look at that, the title even matches up with that. So if we take a look at those pictures there, what do you think? Metals, non-metals? Metals, unless I was being tricky, but I think they were all metals. How about these? Non-metals. See a lot more variability here. This one gets a little bit trickier. And then the last one, what do you think these three are? Somebody's been cheating by looking at the title. Okay. These look, based on the observations that we have access to, they're solids. They have a shiny color to them. And we don't really have any other information that we could look at. Based on that information alone, we might call them metals. It turns out that these three species invalidate some of the metal rules and start to match the non-metals. Well, that's kind of bizarre. Okay? These are a crossover between our metals and our nonmetals. So we refer to them as our metalloids. Okay? If we had some greater classification or some greater organization in, say, maybe a table, we could potentially start to see where these things group. We aren't there yet, okay? But you might start to push down that path. Physical laws. We get conservation of mass. Okay? So what he was able to do in the mid to late 1700s was that he ran some reactions and he noticed that the mass of the reactants he started with always equaled the mass of the products that he ended with. Okay? You may think, well, that's kind of a silly observation. Really? Is it? If I take a block of wood and I light it on fire, what is the weight I have left over? Less than the weight I started with. So the mass changed. Not according to Lavoisier. You can guess how well he was probably treated with this theory. But what did we miss in that observation that the mass of the wood changed? Burning of the wood. What else was produced when you burned the wood? Smoke. Ash. Even if you take the ash, you're not going to get the mass of the wood. What's in the smoke? A gas. That gas being CO2, carbon dioxide, and officially water. That gas phase, traditionally very difficult to trap and keep hold of. Lavoisier was able to build an experiment where he could then control where those products went, and so he could then compare the masses across. Until we have the ability to trap those gases, we can't make this observation. Because every other observation we would expect, burning wood, is counterintuitive to it. Okay? So it's a very neat observation to make. It does have some kind of interesting mathematical principles coming out of it. If I take hydrogen and oxygen and I react them completely with water, start with 2 grams of hydrogen. For those of you that may have the mathematical skills to do all the calculations here, the fancy calculations, please don't do them because I'm making this up. Let's say we had 2 grams of hydrogen reacting entirely with 1 gram of oxygen. What would be the mass of water we should expect? 3 grams. That's the good math I wanted you to do, not the fancy math we'll talk about later in the semester. We have a conservation of mass. The mass of my reactants must equal the mass of my products. In your guess here of 3 grams, you've already made some simple observations. Number 1, these were reactants. And number 2, this was a product. And number 3, we did a reaction with that little arrow in our conversion from reactant to product. Okay. What happens if we take a look at, say, this? I had 5 grams of water produced, but I only started with 2 grams of hydrogen. How many grams of oxygen had to have reacted? 3. How'd you do that? Okay. We don't know what the mass of the oxygen is, so we get 2 plus x equals 5. Solve for x. X equals 3. Okay. Ready for the last one? It's real fun on this one. 5 grams of wood, 2 grams of oxygen. How much water is produced? What is the mass of water produced? Oop, my fault. Anybody want to venture a guess? Heard 7. It's a new equation. There's no hydrogen in this. The mass of the gas and the water must equal 7 grams. I only wanted the mass of the water. So this has to equal the mass of my water, which I'll say is W, plus the mass of what? What was the mass of gas produced? Shaking your head's a good answer. I like it. You don't know. If you have a more advanced equation where you have multiple reactants and multiple products, we cannot solve for an individual species out of that equation. Okay? We would have to come up with another method to solve for it. All we know is that the total mass of our reactants must equal the total mass of our products. In this case, I cannot answer the question, how much water was produced? What would I need to tell you to allow you to solve for that? The mass of gas produced was 1 gram. What was the mass of water?
6.
That is correct. Make sense? Okay. When we go through and put our individual elements together, we end up with this law of definite compositions. That means when I look at water, if I'm going to make water, we already said the elements that are used to make water. What were those elements? And our water formula is? Which means when I mix hydrogen and oxygen together to make water, how many hydrogens do I need?
2.
How many oxygens? 1. Every time I make water, I have 2 hydrogens, 1 oxygen. This is my definite compositions. What happens if I make it 2 oxygens?
Then you need 4 hydrogen.
I would either need to change the number of hydrogens to make water, or
It wouldn't be water.
it wouldn't be water. What would it be? H2O2, also known as hydrogen peroxide. Not a particularly pleasant compound, okay? At least if you were trying to think it was water. 2 guys walk into the bar. One guy goes up to the bartender, asks for a glass of water. The other guy says, yeah, I'll have that too, H2O. Oh, one guy says, I'll have a glass of H2O. And the other guy says, I'll have a glass of H2O2. First guy's alive, the other guy dies. Da-da-da. I don't tell jokes. Okay. How do we measure this? How do we observe these exact compositions? This is a lot trickier. We can go through very particular circumstances where you can heat a compound and it will decompose to different pieces. You can then determine the mass of 1 or more of those pieces to help back calculate the exact composition of your compound. Okay. Electrolysis also works. We can force electricity into a system to force a reaction to occur. We can again measure the mass of our individual pieces that come out of it and be able to back calculate what our actual composition was. Another really common one that happens in organic chemistry a little bit less frequently now is we can take some unknown organic compound, we can react it with a bunch of oxygen, and then collect the products that come out of it. By looking at those products, we can back calculate how much, where did it go? Carbon, hydrogen, or nitrogen were in our compound. Okay? Not a big deal. I just want to make sure that you're aware that we do have the ability to measure those things. Okay? This is where Dalton comes in, and it'll come in again. You have to come up with some idea of what these individual pieces are. So Dalton went through and started to build one of our very first periodic tables. Lovely periodic table, right? Looks a heck of a lot prettier than the one we've got currently. Okay. But imagine drawing H2O. H2O, let's see, I'm not even sure I can find it on here. Actually, I'm pretty positive I can't. So nobody else knows how to read it, so here we go. H2O. Every time you wanted to talk about H2O, that's what you would have to write. Not H2O, but a circle with another circle filled in with another circle that was empty. Every single time. That would get a bit tedious. Okay? Thankfully, we did come up with symbols eventually. He came up with a bunch of different theories applying to these individual elements and how we could then break these down or reuse these within our laws of definite compositions to generate new compounds. Kind of a neat little process. We advance all the way forward, and we can now summarize all of our individual elements, and this is our periodic table. Ta-da! Lovely. Okay? These are now all of the individual building blocks that we can now use to create anything in the universe that we want. Okay? By changing the amount of each of those elements in each of those particular compounds, or whatever we're trying to make. Okay? We do have some specific categories that come out of this. Solids, liquids, and gases are all classified on the periodic table. Okay? Let's rephrase that, on most periodic tables. When we take a look at the periodic table in the PowerPoint, which of those elements are solids, liquids, or gases? Some of you are already cheating and not looking at the PowerPoint. It's a good idea. But looking at me is not a good idea. The periodic table in the PowerPoint has absolutely no information about solid, liquids, and gases. But the periodic table on the wall that you have access to during every single exam does. Where is that information stashed? The colors of each of the individual elements. How did you know it was the colors and not something else? There's a key. Use the key. If you look at the bottom of it, it says anything that is black font is a solid. Anything that is red font is gas. And anything that is blue is a liquid. We have information about those now. Metals, nonmetals, and metalloids. Okay. Anybody know a metal? Say yes. Okay. Name a metal for me.
Gold.
Magnesium. Gold. I wasn't quite ready for you. Magnesium. Gold. Go again. Tin. Thanks. That was a fun one. There we go.
Copper.
Copper.
Silver.
Silver.
Iron.
Aluminum. Iron. Nickel. Zinc.
Lead.
Come on, guys. You're pretty boring. You're all on the left side of the periodic table. Get to the right side, dang it.
Sulfur.
Why are you shaking your head?
'Cause it's not on
There are no metals on the right-hand side of the periodic table. Okay. So give me some nonmetals.
Nitrogen.
Helium.
Uranium?
No.
No.
Argon.
Somebody else said another one that I couldn't remember.
Oxygen.
Come on. Be more creative. Left side of the periodic table.
Fluorides.
That's still the right-hand side.
You
That
can't
is
go
right.
on the left.
I can't go on the left.
Hydrogen.
I was waiting for it.
No, that's right.
Hydrogen's a tricky one. We'll address that in a little bit. Almost all of our nonmetals are found on the right-hand side of the periodic table. So just by looking at the periodic table, we can start to classify where an element is, what characteristics it's going to have, be it a metal or a nonmetal. Okay. Remember, hydrogen is tricky. It is a nonmetal. We'll explain why it's located where it is much, or 4 or 5 weeks from now. Okay, so later in the semester. How about our metalloids? Remember what we were talking about with the metalloids? They had similar characteristics as our metals, but also similar characteristics as our nonmetals. Where might our metalloids fall on the periodic table? Somewhere in the transition between our metals and our nonmetals. Okay. That exact line on deciding specifically where it is, I've never bothered to memorize, partly because we have the little staircase on our periodic table on our walls, telling us the distinct line between our metals and our nonmetals. If we are to the left of that line, that typically means metals. To the right, what if you're on the line? Sometimes you're a metalloid, sometimes not. For instance, aluminum is found on the line, and aluminum is a metal. How would you know? You just know. It's kind of memorized, unfortunately. Those classifications solely came from looking at those physical properties. So unless you knew the physical properties, you wouldn't know how to classify them. Okay? So don't stress about identifying metalloids. You should be able to identify metals and nonmetals. Okay? questions. Some of these you will have to memorize. That list to memorize is found online. That is our elements for memory. You can ignore that helpful files thing because nobody looked there, so I stopped putting it there. Okay. It was straight off the files site. Download that, look at it. Anybody looked at it already? Is there anything different about the names listed in it? I know, it's kind of a hard observation. Some of the elements are bolded, some of them are not bolded. Okay. That list was a list given to me by another faculty member on what she expected her students to know. I looked at it and went, holy crap, that's a lot of elements to memorize. So I said, I don't really quite believe that. And instead, I went through and bolded the ones that are stupidly important. Okay. If they're bolded, you should know it. Okay? And you should be able to know both the name and the symbol, where it's on the periodic table, so you can find it quickly and easily. The more information you know about those bolded ones, the faster your homework will get in the future with chemistry. Yes, and then I think there was a question. You do not have to have the atomic mass or number memorized, though it's helpful when working calculations. So I wouldn't worry about memorizing them. The ones that you will need to memorize eventually, you'll memorize from using them so much. Okay. Why not bother to memorize those numbers? They're on the periodic table, so you don't need to worry about memorizing the exact numbers. Was there a question? Compounds and chemical formulas. Anybody know the formula or what this compound is? You might have used it this morning.
Caffeine.
Caffeine. We got the formula for caffeine up here. Big complex looking thing. We can see all the individual elements within it. We can even see these weird lines connecting things, those weird lines representing bonds, how the individual atoms are connected. You notice in some cases we have single lines versus double lines. What does that mean?
Double bond or single bond.
Single bond versus double bond. Okay. What do those lines represent and how do we use them? We learn when we talk about Lewis structures. You won't ever have to deal with this one unless you want to talk to me about organic chemistry. Okay. This can be a very difficult thing to look at. Okay. But it is extremely helpful because I can now see something about where the atoms are located. Well, does the location of an atom matter? Does the location of your mouth on your body matter? If your mouth was located somewhere else, you might not be so happy all the time. Okay? The location is incredibly important, which is one of the reasons why I don't like general chemistry, because we ignore the location and we focus just on the individual elements, and what we instead look at are formulas. H2O, not the structure of H2O. What does that formula tell us? Well, if we look at the structure, it tells us that there are two H's, one O. How do we know there's only one O? The subscripts immediately after each of our symbols represents how many of the previous symbol in front of it. So if we move to the next one, next one's not very helpful. Let's try that. How many carbons are in that structure? 6. But I see 3 6s. All of those 6s happen to be after, 3 6s, after carbon. Why do they not all count for carbon? It's only what's immediately in front of it. Okay? The 6 applies only to that carbon, only to that hydrogen, only to that oxygen, never to anything else. What is the difference between, I don't know, did I do it right? Let's see. 6? No, I did that wrong. Let's ignore that. We'll come back to that because we're already beyond time. Okay? But we'll pick up there looking at our compounds and chemical formulas, get you an idea of what's happening with that. We'll move into our chemical and physical properties and other fun stuff.